In this video, we are going to be looking at the ionization of water, or Kw. Now, something to keep in mind is that water does not necessarily break down into its ions at like a ridiculous rate. We don't want water to be breaking down into hydrogen and oxygen all the time, but it does. So if we had 550 million molecules of water, only one out of those molecules will dissociate. This is a really small number, but it does account for some, let's say, hydroxide in acids or some hydronium ions in bases. So let's say we had 10 million liters of water. This would be about 1 gram of hydrogen ions and 17 grams of hydroxide ions. Very, very, very small. So, nevertheless, we're going to do two examples, one easy and one sort of next level, to look at this topic, see how we can use that ionization of water. So, we have our formula, Kw is equal to the product of the hydronium or the proton and the hydroxide. This is a constant, this equilibrium constant, 1 times 10 to the negative 14. It does not have units, and it's always this. Always, always, always. So what we want to do, we always have this value for K at 25 degrees Celsius at standard room temperature, or standard temperature and pressure. So we're going to be just identifying what's given in the question, what's required. So we've been given 0.05 molar solution of HCl. If we think about HCl and how it dissociates, it'll break up in sort of a 1-to-1 ratio. So for every mole of HCl, we'll get 1 mole of the proton out. So we can use this value here in our equation. The hydroxide ion concentration, that is what we're looking for. So we're just going to put an X. And then this guy, sort of simple, just try to solve for X. Instead of multiply, we'll do divide. And we'll make sure we do that on both sides. Now, to be honest, this is the tricky part with your calculator. Where you're trying to get this number out. What does it really look like? And I'm just going to, every calculator is a little bit different, so you're going to have to play with your own, just using the calculator on a computer. I myself would use brackets, so 1.0. I would use the multiply sign, the 10, the exponent sign, and then for myself I would type a 14 negative, but just make sure it goes in as negative 14. Close the brackets, and then a divide by your value. So that's how that would look to me on a computer calculator. And so what we've found is 2 times 10 to the negative 12. That's like really small moles per liter of hydroxide at equilibrium. That one's not so bad. What does get a little bit tricky is when we're dealing with mass. So here, originally we were given moles per liter. In this question here, we're not given concentration, we're given grams. So we need to be able to figure out how much does 1 mole of hydrogen bromide weigh. So we're going to have to look at the chemical formula, look on our periodic table what the molar mass is. So again, we're getting this from the periodic table, and this is the number of grams in 1 mole for the substance. If we add those guys together, we'll see that 1 mole of HBr weighs 80.9 grams. Now we've been given 100 grams of this substance. So let's figure out how many moles we have. Now, there's a lot of different ways to do this. I'm just going to use a ratio method. So we've just found out that 80.9 grams is the same as 1 mole. So 100 grams is the same as X moles. For myself, I would be cross-multiplying at this point. So X times 80.9 and 1 times 100. And then try to divide by 80.9 here. Which would leave me with 1.236 moles. So just to kind of keep in mind, what does this mean? It means that in 100 grams of hydrogen bromide, there's 1.236 moles. Now, that number of moles was dissolved in 500 milliliters of water. So we're going to have to find out what the concentration is. So we'll take that moles and divide that by 0.500 liters. So it's not how many moles in 1 liter, we only have a half of a liter. So we'll find out that this is equal to 2.472 moles per liter HBr. So if we dissociate that acid, strong acid, it's going to again break up into a 1-to-1 ratio. So we could say that the concentration of H is also 2.472 moles per liter. So if we have 2.472 moles per liter HBr, we will also get 2.47 liters of moles per liter of the proton. So now we're going to try to figure out our OH value, which is going to be coming from our Kw. So maybe I'll just change my pins. 1.0 times 10 to the negative 14 is going to be equal to, we'll substitute this value for the H plus and the OH, concentration of the OH ions, what we're trying to solve for. So we'll divide both sides. Again, this is really quite tricky on your calculator, but once you've figured it out, try these calculations for yourself. Make sure that you can actually get the value, then you'll be gold. It's also interesting to see how do they represent this. 4.0 times 10 to the negative 15 moles per liter. So a very, very, very small amount. A very small amount is actually present when this dissociates. Most of it will be your hydronium or the proton. Very little of it will be hydroxide, given that it's a strong base.